Quarter 1 review. You can access this video and this review at srhschem.wikispaces.com or on YouTube channel LEFFELlabs. The first questions are about the models of the atom. During his cathode ray experiment, Thomson found that cathode rays are attracted to the positive end of a magnet. Based on these results, how did Thomson modify Dalton's atomic theory? So Thomson performed many cathode ray experiments using a cathode ray tube. This is a tube that has had the gas pumped out of it, and there is a cathode and anode inside across which voltage is applied, and this causes a cathode ray to appear. So Thomson determined that this ray had a negative charge because when he placed charged plates next to it, he found that it deflected towards the positive plate. He measured the displacement of that cathode ray, and from that he was able to determine that these particles are smaller than all atoms. So he also determined that it didn't matter what the cathode and anode were made of, what metal was used, he always got the same result. So this led him to believe that these particles must be present in all elements. Thomson modified the current model, which was Dalton's billiard ball model, to account for these negatively charged particles. He created an atom that was divisible, made up of subatomic particles. So Dalton's solid sphere model, also called the billiard ball model, consists of hard, indivisible spheres that are the building blocks of all matter. And he based this on observations of many chemical reactions. In Thomson's plum pudding model, he had discovered the electron. So electrons are these negatively charged particles that are found in all atoms. And because atoms are neutral, there must be a positive charge in the atom as well. So the plum pudding model consists of a cloud of positive charge with negative electrons embedded within. This is also sometimes called the chocolate chip cookie model, with that cloud of charge being the dough and the electrons being the chocolate chips that are embedded throughout the dough. Explain how the data from Rutherford's gold foil experiment led to the modification of Thomson's plum pudding model. So Rutherford wanted to test the plum pudding model. So he devised an experiment where alpha particles would be shot at a thin layer of gold atoms. So he took an alpha particle source. Alpha particles are emitted by the radioactive decay of a radioactive isotope. So he put this inside of a lead shield with a hole in it, so the alpha particles could only go through the hole. He pointed this alpha particle source at a thin piece of gold foil, and all around the gold foil is a fluorescent screen. Whenever an alpha particle collides with the screen, he would see a flash of light. So he would know where those alpha particles were traveling based on where the flashes of light would appear on the screens. Alpha particles are kind of like atomic bullets. They're positively charged. They're made of 2 protons and 2 neutrons. So if the plum pudding model of the atom was correct, any alpha particles that were shot at the gold foil atoms would pass directly through. So he expected that all of the alpha particles would more or less go through in straight paths through that gold foil. He thought there might be some deflection due to the cloud of positive charge, but for the most part, those alpha particles should go straight through because they're not going to encounter anything that would cause them to bounce back or deflect. Instead, when he performed the experiment, he was surprised to see that some of those alpha particles were deflected, and some of them even bounced back at the alpha particle source. So he said, whenever this happened, that it was as though he had shot a shotgun at a piece of tissue paper, and the bullets, the shrapnel, had come back at him. So this was very surprising to him. This led him to conclude that the atoms have a dense, heavy nucleus with a positive charge, and the rest of the atom is empty space with electrons flying around inside. So because the atom is mostly empty space, those alpha particles generally went through, but about 1 in 8,000 would interact with the nucleus and be deflected back at a wide angle. Compare Thomson's plum pudding model to Bohr's model of the atom. So, in the Bohr model of the atom, electrons are orbiting in energy levels around the nucleus. In the Thomson model, the electrons are simply embedded and static in a positive cloud. The nucleus is made up of protons and neutrons. And in the Thomson model, the charge is just distributed, the positive charge is just distributed as a cloud. The Bohr model has energy levels, so electrons can absorb and emit energy. And when they absorb energy, they'll jump up in energy level, and when they emit energy, they jump down in energy level. So this explains bright line spectra and the flame test. So in summary, the Thomson or plum pudding model of the atom has no nucleus. Instead, there's just this cloud that has a positive charge. The Bohr model, also called the planetary model, has a dense nucleus that is made of protons and neutrons. In the plum pudding model, the electrons are embedded within the cloud. And in the Bohr model, those electrons are orbiting in energy levels. Both the plum pudding model and the planetary model both contain subatomic particles, so they both contain electrons. The next questions are about atomic structure. The subatomic particles that make up the atom are protons, neutrons, and electrons. Protons are positively charged and are found in the nucleus. They have a large relative mass. The neutron has no charge, and it is also found in the nucleus, and its relative mass is also very large. The electrons are negative, and they orbit the nucleus in an electron cloud of high-speed moving electrons, so high-speed negative particles. And electrons are about 2,000 times smaller than a proton. Which subatomic particles account for most of the mass of the atom? So most of the mass is coming from the nucleus, which is made of those big, heavy protons and neutrons. This is why the mass number is the sum of protons plus neutrons. If the electron were to weigh 1 pound, each proton and each neutron would weigh 2,000 pounds, would weigh a ton. So if an electron was the size that's on the screen, then a proton or neutron would be 2,000 times bigger. The next question has a chart that is about atomic structure. So in order to complete this chart, you need to keep a few things in mind. First, atomic number is equal to the number of protons. You can remember this by thinking of AP Chem. Atomic number, number protons. So this is always going to be the same for a given element. Carbon will always have 6 protons, otherwise it wouldn't be carbon. The mass number is the sum of protons and neutrons, and that means that for a given element, the mass number can change based on the number of neutrons. In order to determine the charge, you need to look at the protons and the electrons. So add up the positive protons and the negative electrons, and what you get is going to be the charge. So for a neutral carbon atom, 6 protons, so that's plus 6, and if you add that to negative 6 electrons, you get a charge of 0 or neutral. Cation has a positive charge, anion is a negative charge, and a neutral atom has no charge. So whenever we write the symbol, we put the symbol is the abbreviation from the table of elements. The mass number is on top, the atomic number is on bottom, and we also write the charge. So here I have 3 neutrally charged carbon atoms. These are isotopes. They have the same atomic number, but a different mass number. So they all have 6 protons because it's carbon. But the mass number is different because the first one has 6 neutrons. 6 and 6 make 12. The second one has 7 neutrons. 7 and 6 make 13. And the last one is going to have 8 neutrons. 8 plus 6 make 14. So in our table, the symbol gives us everything that we need to know. The number on bottom is the atomic number, which is equal to the number of protons. The number on top is the mass number. So 35 protons plus some number of neutrons should equal 80. So in order to total to 80, I need 35 protons and 45 neutrons. The charge for this particular bromine atom is 0, which means that I must have an equal number of protons and electrons. This atom is neutral. For the next one, the atomic number is 30, which means that I've got 30 protons. The mass number is 67, so 30 protons plus some number of neutrons should equal 67. So I need 37 neutrons. The charge of this atom is -1. That means that I've got to have one more electron than protons. If I do plus 30 plus negative 31, that gives me a charge of -1, and this is an anion. So my symbol is going to be zinc. I know this because the atomic number is 30. Charge is -1, and my mass number is 67. The next one has an atomic number of 17, so that's going to be 17 protons. There are 17 protons and 19 neutrons, so this makes a mass number of 36. And because the protons and electrons have equal numbers, this is a neutral atom with 0 charge. So my symbol is going to be chlorine, because that's atomic number 17. My mass number is 36, and the charge is 0. My next atom has 30 protons, so I can conclude the atomic number is also 30. The mass number is going to be 66 because I need to do 30 protons plus 36 neutrons. My mass number is 66. My charge is +1. So that means that I got to have one less electron than protons. So positive 30 protons plus negative 29 electrons gives me a charge of +1 for this cation. Again, I have zinc because my atomic number is 30. This time my charge is +1 and I have a mass number of 66. The last atom has 28 protons, so the atomic number is 28. The mass number is 62. So 28 protons plus some number of neutrons is going to give me a mass number of 62. So I need to have 34 neutrons. I have 2 more electrons than protons, so my charge is -2. This is an anion. The symbol is nickel because the atomic number is 28. My mass number was 62, and my charge was -2. Which pair of atoms in the chart represent a pair of isotopes? So isotopes are atoms of the same element that have different number of neutrons. In other words, the atomic number, the protons, is the same because it's the same element, but the mass number is different due to a different number of neutrons. So in the table, there was a pair of zinc isotopes. So they both have 30 protons. The atomic number is the same because they're both zinc. One has 37 neutrons and the other has 36. One's also a cation and one's also an anion. Which of the following would have more electrons? Iron with a +2 charge or iron with a +3 charge? So in the table, there are several iron atoms which all have different charges. Since they're all iron, they all have 26 protons. The first one has a 0 charge, which means that the electrons and protons must be equal. The second one must have one less electron than protons because the charge is positive 1, and it's lost 1 electron. The last one must have 23 electrons and 26 protons to make a +3 charge, so it has lost 3 electrons. So the more positive, the fewer electrons, which means that Fe plus 2 has more electrons. Based on the bright line spectra, which elements are not found in the mixture? So in order to do this, you need to compare the lines. So first, if we compare strontium to the mixture, we see that all of those lines are present in the mixture. We can also compare lithium, and we see that all of those lines are present. So no cadmium is present in the mixture because we are missing those spectral lines. The next question is about the movement of electrons between energy levels. So here I have a Bohr model of the atom with 1 electron orbiting the nucleus. That's in the first energy level. Now that electron can absorb energy, causing it to jump up in energy level to the excited state. To get back to the stable ground state, the electron needs to re-emit that energy. And sometimes, depending on the amount of energy that is emitted, we might see it with our eyes as visible light. So when emission occurs, that electron emits energy and returns down to the ground state. When an electron absorbs energy, it will jump up in energy level. To regain stability, the electron will emit energy, causing the electron to jump down in energy level. The emitted energy may be seen as visible light. Now we have a table with electron configuration. So the fluorine atom has a total of 9 electrons. 2 are in the first energy level, and the second energy level, which is split up into s and p orbitals, has a total of 7 electrons. So that second energy level was my highest energy level, so that's the valence shell. Sodium has 11 electrons, so it goes into the 3s orbital, making 3s1 my valence shell, and I have 1 valence electron. Argon has 18 electrons, and its electron configuration has a third energy level with a total of 8 electrons in its valence shell. So this is a noble gas. It has a full octet of full 8 valence electrons. This explains why these noble gases are not very reactive, because they already have a full octet. The notable exception to that is helium. Helium is a noble gas, but it only has 2 electrons because it only has that 1s energy level. So using the electron configuration, explain why sodium and potassium are going to have very similar chemical properties. So here's the electron configuration of sodium and potassium. Valence electrons are what determines the chemical properties of atoms. Atoms react to form compounds by transferring or sharing these valence electrons. So because sodium and potassium both have 1 valence electron, they will react in the same manner, giving them very similar properties. They're both alkali metals, and they share a column because they have those very similar electron configurations, especially in their valence shell. The next set of questions are about periodic trends. So how did Mendeleev organize his periodic table, and what order are those atoms in the modern periodic table? So Mendeleev organized his periodic table based on the properties of each element. For example, how it reacts with oxygen, how it reacts with hydrogen, what happens when it is added to water. So he used a lot of these properties to organize his elements. The modern table of elements is arranged by increasing atomic number. So when the elements are arranged in this manner, the properties repeat in a periodic fashion. and this periodic fashion is predictable. Explain the difference between a group and family and a period/series. So a group or family is a column. This runs up and down, and it all starts with letters at the beginning of the alphabet. So group, column, family, all the same thing. A period or series is going to be a horizontal row. And period, series, and row all start with letters at the end of the alphabet, so you can remember that they're all the same thing. And those run left to right. What is the group name for each of the following elements? So potassium is in group 1, making an alkaline metal. Fluorine is in group 17, making it a halogen. Strontium is in the second column, making it an alkaline earth metal. And xenon is in column 18, the last one, making it a noble gas. So for each of the trends, let's explain what happens as we go down a group and across a period. So atomic radius, this is from the center of the nucleus to the edge of the electron cloud. As I go down a group, we're getting more energy levels. So I'm getting more layers of electrons, and this means the radius is getting larger. As I go across a period, that nucleus is becoming more positive. I'm gaining protons. So that means that those electrons are more attracted to the nucleus. They move in, and the radius gets smaller. Ionization energy is how much energy do I need to remove that outermost electron. So how hard do I have to pull? How much energy do I need to rip off that electron? This all comes down to attraction. So if it is the electrons are very strongly attracted to the nucleus, I'm going to need a lot of energy to pull one away. If the attraction is weak, then I need less ionization energy to pull that electron away. So as I go down a group, I get more energy levels, so that attraction is weaker. Those electrons are farther and farther away from the nucleus, so I need less ionization energy. Across the period, however, that nucleus is gaining protons and it's becoming more positive. So that attraction is stronger and I would need more ionization energy to pull off an electron. Electronegativity is a measure of attractiveness. How strongly does that atom attract electrons when in a bond? So as we go down a group, I'm getting more energy levels, weaker attraction between nucleus and electrons. Those electrons are now farther away from the nucleus, so my electronegativity is lower as I go down a group. Across a period, the nucleus is gaining protons, it's becoming more positive, and the attraction is getting stronger. So that causes a higher electronegativity. Metallic character is how easy it is for the atom to lose electrons. So metals are metals because they lose electrons easily. This explains the properties of metals. They're shiny because those electrons that the atoms lose get shared in an electron sea that easily absorbs and re-emits light as per the Bohr model. So your eyes see that as shininess. So metallic character is going to increase as it is easier to lose electrons. So as you move down a group, we get more energy levels, which means that there's more shielding, that attraction is getting weaker. So it's easier to lose electrons and the elements become more metallic as we go down a group. Across a period, the nucleus gains protons and it becomes more positive. So the electrons are going to be more strongly attracted to the nucleus and it's harder to lose electrons. So as we go across a period, we become less metallic. This makes sense if you look at the periodic table. You can see where the metals and the nonmetals are. And as you move towards the right side of the table, that's where all of the nonmetals are. So, metal, nonmetal, and metalloid. So the metal examples are things like magnesium and sodium, which is in blue on my table here. That's most of the periodic table. My nonmetals are in yellow, like carbon, nitrogen, and oxygen. And my metalloids are in green. It's important to note the staircase that's formed by the metalloids. So pretty much everything that touches that staircase, except for aluminum, is going to behave like a metal. The ones at the bottom, there's some debate. There's no formal definition for a metalloid. So some people consider them metals, some people consider them nonmetals, and some people consider metalloids. But more or less, those elements that are in green, those are the ones that don't quite behave like a metal, and they don't quite behave like a nonmetal. Circle the elements that would have the most similar properties. So the closer together elements are, their position on the periodic table, the more alike they're going to be. And this is due to the fact that they have similar valence shell configurations. So elements that share a column are going to have the same valence shell configuration, giving them very similar properties. So of the ones presented, fluorine, chlorine, and bromine are all in the same column. They're all halogens. They all have very similar properties. So compare the properties of metal, metalloid, and nonmetal. So metals show delocalized bonding. Those electrons are shared in an electron sea between all atoms. So this explains why metals are shiny, malleable, ductile, and good conductors of heat and electricity. Nonmetals have completely localized bonds, meaning that those electrons are shared between only two atoms. So they have the opposite properties. They're dull, they're brittle, and they're going to be poor conductors of heat and electricity. Metalloids have bonding that's kind of in between the localized and delocalized. So we get properties that are in between metals and nonmetals, or maybe they have some of each, but most notably, metalloids are going to be semiconductors. This is why they're used in a lot of computer chips, electronics. Silicon is typically used in computer chips because of the fact that it is a semiconductor. Question 21 involves using the graph to answer some questions. So first we can complete the graph by connecting the dots. So this is showing us a trend in ionization energy. And we can see that as the atomic number increases, that ionization energy is decreasing. So based on the atomic number, so atomic number 3 is lithium. So there's lithium on my graph. It corresponds to that point. And we can estimate the ionization energy is about 510 kilojoules per mole. Sodium is atomic number 11. So there it is on our chart, and it's about 500 kilojoules per mole of ionization energy. We don't see potassium on the chart, but we do see atomic number 37, which is rubidium, and it's got about 400 kilojoules per mole of ionization energy. And we see cesium, which is atomic number 55, and it's got around 380 kilojoules per mole. So potassium, which isn't on the chart, is atomic number 19. So I can go ahead and place a dot on atomic number 19 on that line which is showing me the trend. So based on this, we can predict that potassium is going to have an ionization energy in between sodium and rubidium. So maybe around 450 kilojoules per mole. Cations are smaller than the neutral atoms they form from, while anions are larger than the neutral atoms they form from. So cations lose electrons, causing the remaining electrons to feel a stronger attraction to the nucleus and move in, causing the radius to be smaller. Anions, however, gain electrons. So with the addition of these extra electrons, there's going to be a weaker attraction to the nucleus, and those electrons would move out, causing the radius to increase.